Now we talk about built-in self-test. So, a technique whereby a chip can test itself. Let us see the salient features, what are the requirements, and then we shall see how we can achieve this to some extent. I mean, we cannot do as good as external testing, but what best we can do, let us see that. So, the basic concept behind built-in self-test is to add some additional hardware inside the chip, such that test generation and response evaluation can be done inside. Okay. Let us see what is the conventional approach, what we do. The conventional approach is that I am just trying to show it diagrammatically here. So, I have a circuit under test CUT. I have a functional specification. Okay. There are inputs, there are outputs. So, what I do, I use a tool first. I use a test generation tool, where just as the input I shall be providing with this circuit netlist, let us say, or this some kind of specification, and the test generation tool will give me a set of test vectors T. Now, this is done once. Now, once the circuits are manufactured, what we do is we use something called an automated test equipment, or ATE. We load the test patterns in the ATE memory, and the ATE will be generating these inputs to this chip, which will be sitting on the ATE, and similarly the outputs will be fed here. So, ATE will be in control of applying the test patterns and evaluating the response. Now, the point to note is that this ATE is an extremely expensive equipment. Well, although we use it, but the total cost of manufacturing also has a component which is the cost of the ATE. Okay. So, this is the more conventional approach, but here our test generation and response evaluation both we are doing inside the chip itself. Okay. So, we are not relying on an external test generator to generate the test. Maybe we are using something or some external ATE to apply the tests. Naturally, to do this on chip, we need additional hardware. Okay. So, suppose we have implemented this kind of extra facility inside the chip, so that it can test itself, BIST. So, to control the BIST operation, we need a minimum of 2 pins. So, there will be one pin which we will like test control. So, here we will be telling the chip that, well, now you test yourself. That pin, if activated, will cause the chip to start the testing, and that will happen internally only with no external intervention. And once the testing is over, there will be an output pin saying good or bad. It will tell that, well, I am good or I am bad. So, BIST normally will not tell anything more than that. It will just tell either the chip is working good or there is something wrong that has been detected. Okay. So, this is how now the inside of my chip will look like. Earlier we had only our circuits under test, but now we have a test generator, we have a response compactor. We shall come to this a little later, why we need this. And externally, as I said, we need one control signal to start or activate the BIST operation, and we need one control signal to evaluate the result of the test. Okay. All right. Let us now look at the motivation. Why do we need BIST and what are the advantages? The first one I already mentioned, that we do not need an expensive automated test equipment. You see, this AT is a very sophisticated equipment, it is a bulky equipment, it has to be installed in a very controlled environment. So, when you want to test a chip, you have to go near the ATE, put it on the ATE, and ATE will be just applying the test vectors and test it. But now, if we have BIST feature in a chip, it is not necessarily to go to the ATE to test the chip. You can even test it in your lab, that is your field. So, can be used for field test. Diagnosis means you are trying to identify which chip is bad. Diagnosis is the identification of the source of failure. Okay. So, normally in a system we use something called software tests. Like you might have seen in a desktop or a laptop, when you turn on the machine for the first time, there is a software diagnostic which starts running. That is a software program. So, it does some routine checks, it checks memory, etc., and if it finds that something is wrong, it reports with a code. So, you will have to decode what that code means to identify what or which subsystem is not working correctly, right. Now, BIST can be an alternative to this kind of software tests. But the software tests, the problem is typically software tests, they carry out testing in a very loose and abstract way. The fault coverage in terms of the hardware is pretty low. The diagnostic resolution is also pretty low. Sometimes it will only say that there is a fault on the motherboard of your PC, but where in the motherboard, that it does not say. Okay. And also because it is a software program which is running, it will be more time consuming. But in BIST, we are trying to do this in hardware, and if you do this, the advantages are, of course, the test effort will be lower because the time taken will be less. Diagnosis will be better because chips, at the chip level you can do the testing, and since you can do it on field, your system maintenance and repairing costs will be also much less. So, instead of every time there is a failure you have to go to one place to find out the source of the fault, you can do it in your own small lab also. Okay. Fine. Now, the BIST architecture overall, it looks like this. So, I have my circuit under test which I want to test. So, what are the components I need? So, this whole picture is something that goes inside the chip. Of course, I need a pattern generator, so which will be generating my test patterns. Now, you can argue that, well, I have a very good test generator, it can generate some very good small set of test patterns. Let me keep it in a ROM and let the ROM be inside the chip. But it is possible, but the overhead of that ROM will be much higher. For some circuits, you may find that you need 1000 test vectors. So, you need a ROM with 1000 words just to store that, right. And of course, the access time of the ROM will be slower as compared to hardware. So, typically what is done, this pattern generator is some kind of a hardware structure which can run very fast and generate some patterns which will be used for testing. So, this multiplexer will be selecting whether you are in the normal mode of operation where this primary input should go in, or you are in the test mode where this patterns should go in. Okay. Similarly, here in the normal mode, the output of the circuit will go to the PO, the primary outputs, but during the test mode, you have something called a response compactor inside the chip. Let me just explain this. Well, again let us argue that I am applying 1000 test patterns to a circuit, there are 10 output lines. So, I will be generating 1000 bits of information on each of these 10 output lines corresponding to the 1000 test vectors. So, I will be having how many? 1000 each, there are 10 such lines. So, it will be 10 kilobytes of data, that means 100 kilobytes of data, sorry 10 lines into 1000, yes, 10 kilobytes of data. So, what you can argue is that, well, I will store these 10 kilobytes of expected response again in a ROM, and when the test is going on, I will compare them bit by bit. But here again I will say that, well, you can do it definitely, but your overhead will be becoming too much. If you are saying that you will be using a ROM to store your input vector, to store your output response, you need a ROM of a very large capacity, large size, because for a modern day circuits let us say, you may be requiring millions of test vectors, and in the circuit there can be hundreds of outputs. So, the volume of test data that you need to store can be pretty huge. Okay. So, you need something called a response compactor, we shall come to this, that will reduce the volume of the test data to a relatively small volume, and you can use a small ROM to store the correct response for that small volume after compaction. So, after compaction you compare the compacted response with the corresponding golden value that is stored in the ROM. So, if they match, you say that your test has passed, it is good. If it fails, you say it is bad. Okay. But there are a few things you see in this circuit, there are a few things which the BIST is not checking, like connection from PI to the multiplex. It is only testing the pattern generation to circuit and circuit to response compactor, but this PI connection, PO connection, if there is any fault here, these parts are not tested. Okay. So, this has to be remembered. Now, okay, random pattern testing is a very important and interesting concept. So far what we have said and seen, we said that we have a circuit, we have a set of faults. Let us try to find out a nice small set of faults that can detect it. Okay, we also said that test generation is complex and it takes time, particularly for larger circuits. Okay. Now, there is an alternative. Here we say that we just forget test pattern generation, we do not use a test pattern generator at all. Let us use some kind of random patterns. Well, random patterns means there will be purely random patterns, but what we generate are actually pseudo random patterns. Pseudo random pattern means patterns which can be repeated in time, and these pseudo random patterns are typically generated using a hardware structure which is called linear feedback shift register or LFSR. So, what we can do, we can use an LFSR, it is a very simple hardware structure, say we can generate 1000 random patterns, and using fault simulation we can find out that using those 1000 test patterns, random patterns, what is the fault coverage, how many percentage of faults are getting detected. So, if you see that our fault coverage has reached an acceptable value, we can say that, well, let us use this many patterns. I am giving an example. Suppose you find that your desirable level is reached only after applying 1 million test patterns. You see, for a conventional test generation, this 1 million was a very large number, because 1 million patterns have to be generated, stored somewhere in AT, you will have to load this pattern in AT memory. But here I have a LFSR which will be simply running for 1 million clock cycles, there is nothing to store anywhere, right. And say means if I use a clock frequency of 1 gigahertz, then this 1 million pattern will take only 1 millisecond of time to be applied, right. So, here time is also not that much of an issue. So, you need to see this, or remember this also. So, the test length can be larger, but the test generation is very trivial, and we can continue until either we reach a desired level of fault coverage, but sometimes it is not applicable to BIST. We can see that beyond a point we are not able to detect faults anymore, then for the remaining faults you can switch to an ATPG tool. But for BIST application we do not do this, we do pure random pattern testing usually. Okay. So, the behavior of typical circuits is like this. So, as I go on applying number of pseudo random test patterns, these are the number of test vectors I am applying pseudo random. So, through fault simulation I am continuously monitoring the fault coverage. The typical curve is like this. So, it will go on rapidly increasing, but beyond the point it will more or less level off. So, if you can identify this point, then you can say that well, this is my optimum number of test vectors, I will apply so many. Okay. Now, this number will depend or vary from circuit to circuit. So, for a given circuit, so just using fault simulation you will have to find out the value, right. Okay. Now, let us see what is a linear feedback shift register. Now, LFSR is, as the name implies, it is some kind of a shift register. It is a hardware circuit based on a shift register. There is a feedback circuit also, and the feedback circuit is linear feedback. Okay, here we are not going into the mathematical detail. This feedback circuit consists of exclusive OR gate, and XOR function can be proved to be a linear function. That is why it is called linear feedback. And LFSRs has been found to be a very good source of pseudo random patterns and has been used in many applications. Random pattern generation is of course one application, but many of you may have heard of cyclic redundancy check, which is used for error checking. For communication, when you store some data on hard disks, everywhere there can be errors. CRC is a very common and popular way to detect errors. Okay. And here again we use an LFSR to generate some kind of a CRC checksum or signature. Okay. And we will see later that when we talk about the compaction of the responses, there also again we can use a LFSR. This we will see later. So, how does an LFSR look like? So, there are two alternate structures of an LFSR, type 1 or type 2. Type 1 is the classical structure where you can identify the feedback. This is an XOR gate. You see D1, D2, D3, D4 are, these are flip flops connected as a shift register, these are D flip flops. So, the output of the last flip flop is fed back to the input of this XOR, and some other output like here D1 is also fed as the input of XOR. So, here I have a choice, I can use this, I can take from D2, D2, D3 or all of them together, and output of the shift register is fed as the input to the first flip flop. So, you see this LFSR does not have any external input. So, once you load it with an initial value and apply the clock, it will go on running in an autonomous fashion, it will be generating some patterns continuously. So, there is an alternate structure of LFSR which is used more commonly for data compaction, where instead of using XOR in the feedback circuit, we do like this. We use the feedback directly, but we can use this XOR gates somewhere in between, and whenever you use XOR gate, you also take one of the inputs from this line. Okay. Similarly, there can be an XOR gate here. So, one input will come from here, one input from here, like this. So, this is called type 1 LFSR, type 2 LFSR. So, let us take the example of generating a pattern using an LFSR. So, let us take a type 1 LFSR like this, where I have 4 flip flops, a 4-bit LFSR. The feedback connection is like this, from D4 and from D1, the output of the XOR is fed to D1. Now, the behavior of an LFSR will depend quite a lot on the points from where you are taking the feedback connection. Now, this feedback connection or the structure of this LFSR can be defined by something called a characteristic polynomial. Like this particular LFSR is represented or characterized by this polynomial. What does this mean? You see, x to the power 4, x is a parameter, x to the power 4 represents this, x to the power 4, x to the power 3, x to the power 2, x to the power 1 and x to the power 0. So, here we have a connection from x to the power 4 and x to the power 1, that is why these two terms are there, and 1 will always be there because you are connecting to x to the power 0. So, if instead of this there is a connection from here, then instead of x to the power 1 this would be x to the power 2, x square. If there is a connection from here, it would have been x cube. Okay. So, depending on your tapping points from where you are connecting to the input of the exclusive OR, your characteristic polynomial will vary. This is called characteristic polynomial. Now, let us see the patterns which are generated. Okay, this D1 should be here, D4, D3, D2, D1. Suppose we are initializing the LFSR with 1 0 0 0, 1 0 0 0. So, as we apply clock, there will be a shifting and a new bit will be getting in, which will be the XOR of D4 and D1. So, this is D1 and this is D4, right. So, you go on shifting like this, D4 and D1 0 and only 1. So, next time you shift it, this 1 will get shifted in D1, next 1 and 0. You shift, again 1 will be shifted. So, 1 1, 1 and 0, again 1 will be shifted, 1 1 1, again 1 0, again 1 will get shifted, but now 1 and 1 0, XOR is 0. So, now 0 will be shifted, 1 and 0, again 1 will be shifted, like this. You see, as you go on applying clocks, you will see some patterns are being generated, and after a certain number this 1 0 0 0 is repeating. So, again after 1 0 0 this same pattern will come again. So, let us count the patterns 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 patterns have been generated. 15 patterns are generated before repeating. So, can you guess which pattern is missing here? The all 0 pattern is missing. You see, for LFSR the all 0 pattern has a very, you can say, dangerous implication. Like once you load this LFSR with all 0 pattern, it will remain in the all 0 state, because XOR of 0 and 0 will be 0, 0 will be shifted. So, right shift and 0 comes in, so it will remain all 0. So, whenever we are wanting to use LFSR for a data generation application, we should never load it with all 0, and this is a very good kind of LFSR we have chosen, because we are able to generate all the other 15 patterns excepting 0. Okay. And if you look at the decimal equivalent of these numbers, 8, 1 0 0 is 8, 1, 3, 7, 15, 14, 12, 10, 5, then 11, 6 and so on. These numbers look random. Now, there are some standard tests for randomness. So, people have evaluated the patterns which are generated by LFSR with respect to randomness, and it has been found that the randomness quality is pretty good. Other than one test which fails, the other tests pass quite satisfactorily. Okay. So, even if you want a serial bit pattern, you take the output of any one of the flip flop, this is also random, 0 1 1 1 0 1 0 1 1 0 0 1 0 1, this is also a random pattern. Okay, you can either take a parallel pattern as random, or serially you can take the output of any one of the flip flop. But only one test, as I said, which is not satisfied with respect to randomness, is that because the basic structure is a shift register, you will see there is a pattern diagonally 0 0 0 0, these are getting shifted 1 1 1 1, okay, these are getting shifted, right. So, this is called cross correlation among the different bits. This is one property where it fails. Okay. Now, some definitions of LFSR. Now, we had taken in this example a 4-bit LFSR and we had seen that we had generated 15 patterns. So, in general for an n-bit or n-stage LFSR, so we can have at most 2 to the power n minus 1 patterns generated. Such a sequence generated by an LFSR where all the patterns other than the all 0 pattern are getting generated, that is called a maximum length sequence or an M sequence. Now, the characteristic polynomial like in this LFSR, the tapping points they define the characteristic polynomial. So, the characteristic polynomial which generates an M sequence is called a primitive polynomial. Now, for this example, this was a primitive polynomial, that is why 15 patterns were generated. So, there is another definition, that irreducible polynomial is a polynomial which cannot be factored. Now, primitive polynomial is a type of irreducible polynomial. So, there are ways to identify this kind of primitive polynomials. There are comprehensive lists of these primitive polynomials available in various places. So, I am showing here a few. This number indicates the number of flip flops, that means number of stages in the LFSR, and this is kind of a coding from where you are taking the taps. 310 means you are taking the tap, of course from the last stage 3 will be there, and from 1 and 0. So, the polynomial will be x cube plus x plus 1. For 4, x plus 1. Similarly, for 16, this 32, this 64. So, you see, so if you take a 32-bit LFSR with a primitive polynomial like this, that means there will be these many tapping points, then you can have a circuit which can generate 2 to the power 32 minus 1 patterns, that means 4 billion patterns. You have a very convenient circuit which can generate 4 billion random patterns. Okay? So, it is a big advantage. So, these M sequences also have some interesting properties, like as I said, firstly the period before it repeats is 2 to the power n minus 1. That means the bit a p plus I will be equal to a I for p equal to n minus 1. It repeats after p. Starting from any non-zero state, the LFSR will go through all the other 2 to the power n minus 1 states before repeating. This we have already seen. Number of ones differ from number of zeros by 1. So, if you look at the output column for any of the bits, see, for a normal truth table where you have all 2 to the power n, number of zeros and ones are equal. Now, here we do not have the all 0 pattern. So, now zeros will be 1 less, right. So, number of ones will exceed number of zeros by 1. And here there are some other properties also which are not very important in the present day context. Like if you slide a window of slide of width n across a sequence of bits generated, then each of the binary patterns will be seen exactly once in a period. Like what I mean is that, like you look at this, if you slide a window of with 4 like a 0 1 1 1, then 1 1 1 1, then 1 1 1 0, 1 1 0 1, 1 0 1 0. So, these will be appearing exactly once and uniquely. Of course, there is some other property that it runs. So, here we are not wanting it. Now, randomness properties of M sequence is something which you are interested about here, because M sequences have very good pseudo randomness properties. The autocorrelation, cross correlation is 0, but cross correlation between two output bits, two consecutive output bits is poor, as you had said, because of the shift register connection. So, in a typical test environment like BIST, we can generate as many patterns we require. So, means if I say that I need 1 billion patterns, fine, I can do that. So means with a 1 gigahertz clock I need only 1 second to apply the test, and The good thing is that we are able to test at the maximum clock speed. This is called at speed testing, where some faults which also arise because of delays in the circuit, the critical timings, they will also get detected. In scan designs, we are not detecting such kind of faults. Okay. So, with this we come to the end of this lecture. In our next lecture, we shall be looking at the other part of BIST. So, we have seen the test generation part, but now after we have obtained the responses, how do we compact and compare? That part we will be seeing in the next lecture. Thank you.